Hello, and let's move on into Bayesian inference and how we can get in touch with the Bayes rule applied to statistical inference. Okay, so now that we have cleared the Bayes rule, we can apply it into statistical inference in a very interesting way. So we need to cover that in detail. Okay, so quick recap. This is the Bayes rule. So the main magic and basic usefulness of this rule is that we can obtain inaccessible condition probabilities if we know the inverse condition probabilities and their marginals. Okay, and you can also understand it via a cross table or the generalized form of this cross table. Okay, so now we can dive into Bayesian inference. This approach was developed by Laplace, and we will start like statistical inference is getting to parameter populations using sample statistics that are retrieved from data. And that research questions usually are about if certain parameter has a certain value or not that if the data is likely assuming the parameter has this value. We want the probability of the parameter being of a specific value given the data. The data, assuming that has occurred and we have a grasp upon it because we have a database. Not that the probability of the data being likely under that, assuming the parameter has a certain value. In NHST, the main problem that Bayesian's argument or gets as a case is that the p-value is this inverse probability. It's not getting to the point. We want to know the probability of the parameter given the data, not the probability of the data given the parameter. In addition, NHST implies the probability distribution of H0 is unknowable. In many occasions, actually, we can establish an informed assumption of the distribution of H0, for example, with demographics, previous studies, literature, etc. So these are the two main advantages of Bayesian inference. However, in return, we must assume a degree of subjectivity in choosing the probability distribution of H0. Okay, so if we retrieve the cross tables, we will now can substitute the events as data pointing as yes or no of certain parameter, and the parameter having a value, a real value of 1 or 0, for example, to be really simplistic. So the cross table will have this form, that data being yes, assuming given that parameter is 1 or the parameter is 0. Also, we can get to the generalized form of this cross table, and where now we have all of the probabilities of the parameter having any value that can have. We can also have the probabilities of all of the values of the data and any value of the parameter happening at the same time that can be expressed of the condition probabilities of both of them multiplied by the respective marginals. And also we have the marginal of the data that can be expressed as the sum of the probabilities, the condition probabilities multiplied by their marginals if we have a discrete value or if we have continuous values and integral. Okay, so now the Bayes rule transforms into this. The probability of H0 being true given that the data is what it is can be expressed as the probability of the data being true given the H0 is true, multiplied by the probability that the model is true and divided by the probability that the data is true. Okay, so let's decompose. The probability of the model being true given our data is going to be called the posterior probability. It's the product. To get to this product, we will have the probability of obtaining the present data if the model was true. That is basically the same definition as a p-value, for example, and we are going to call this data likelihood. This is going to be multiplied by the marginal that is called the probability that the model is true. That is called a prior distribution. And finally, we will divide it by the probability that the data is true. That we will call that evidence. Okay? So, expressed with population parameters, this turns into this. The probability, or condition probability of the parameter given data can be expressed as the credibility of that parameter already known in our data. This is the posterior belief, or the posterior probability, can be calculated as the probability of our data occurred under that parameter, data likelihood, multiplying our prior probability or prior belief, that is the credibility of that parameter without knowing the data, and divided by the probability of the data, that can be called evidence or marginal likelihood, can be expressed as a mean of likelihoods of the mean of all probabilities of data given parameter. This is normally not known, so we will use normalizing constants in their place. So actually we can expand the denominator of this quotient, and we can have the marginal likelihood expressed as a sum or as an integral. Okay, so simplifying and to be clear, the posterior probability or the posterior probability distribution can be calculated as the likelihood distribution multiplied by the prior distribution and divided by the evidence or the marginal likelihood. Okay, so just a really quick recap. Remember that the two previous approaches on probability, the classic and the frequentist, aimed at assuming that probability was something that was knowable. The classic is absolutely knowable and the frequentist is approximately knowable, but they are essentially separated from our belief or our subjective state. In turn, Bayesian approach will assume that probability is the expression of a belief on a degree of certainty. This is, I will have a belief that something is at some point likely or certain. I have a degree of likelihood. Therefore, I will have a belief that more or less the degree is like this. The degree of credibility or certainty is like this. I will express that in a mathematical form, for example, in a probability distribution. And therefore, that is a probability. It's the expression of my subjective belief of a degree of certainty. We will have two of them, the prior belief and the posterior belief. The prior belief is my belief in a model being true without knowing the data. That is going to be called this probability of the parameter. And also the posterior belief, that is my updated belief after knowing the data. So it's going to be the probability of this parameter having that value given that the data has occurred. To obtain the posterior beliefs, we need data to obtain that likelihood and specify our prior beliefs in the model. Due to being probabilistic, we need to specify the sampling distribution of our parameter. Therefore, we need to acknowledge explicitly and rigorously our beliefs in the model. We don't need to express them verbally, we need to express them mathematically. For example, this distribution with these parameters, therefore expressing this degree of belief. Therefore, a Bayesian approach is the combination in our minds of the prior belief and the data likelihood to obtain a product that is called the posterior belief. Okay, so these are examples of discrete and continuous distributions. So you can see here that we have a prior belief in a discrete values, then data likelihood is going to have a different shape and they're going to be combined to get a posterior distribution of how the probability of values should be. And this is the same example, but with continuous probabilities. And this is another example that we encounter more than once regarding applied analysis, because it's really common in software to encounter this kind of plots. So you can see the density plots of my prior belief and my posterior belief and see how they overlap or how different they are. Okay, so this is in a nutshell a Bayesian inference.